This is the model of the quick return mechanism that is used in a shaping machine. This is the cutting tool. This tool holder moves in a slot in the frame of the machine. This is what is called the bull gear, which is rotated at a constant speed. And here is a block which is hinged to the bull gear, and this block moves up and down in this slotted lever, and the slotted lever is hinged to the frame at this point, and the slotted lever is connected to the tool holder by an additional link. So we have a 6-link mechanism here where the continuous uniform rotation of the bull gear is converted into the to and fro motion of the cutting tool. Now, the cutting tool during the forward motion is doing useful work, and we have to maintain a proper cutting speed. However, during the return stroke of the tool, this is not doing any useful work, so I would like to make the return faster, and that is why it is called quick return mechanism. As is seen very clearly, if I rotate the bull gear at almost uniform speed, the forward motion is slow, but the return is faster. This is the model of that Whitworth quick return mechanism. Here the cutting tool is this one, which is moving in this horizontal slot. So if we rotate the input link at a constant speed, as is obvious that the forward and return motion of the tool is taking different time. It is going much faster on this direction and coming back much slower in this direction. So if this we considered as the cutting tool which is cutting in that direction, then we should rotate it in the opposite direction. It is cutting slowly and returning much faster. Next, we shall see the kinematic diagram of this Whitworth quick return mechanism and analyze its quick return ratio. This is the of this mechanism which is used for a front-end loader. As we see, there are two hydraulic actuators between link number 2 and link number 3, and there is another hydraulic actuator between this red link and this link, that is link 6 and link 7. By moving these two hydraulic actuators, we can move the front end of this loader, that is this bin, which is link number 9. We'll first show that this particular mechanism has 2 degrees of freedom and with 2 inputs here and there through these 2 hydraulic actuators. Consequently, this output link cannot go anywhere with any arbitrary orientation. It will have only 2 independent coordinates which you can specify, either the xy coordinates of a point on it and the orientation will be automatically fixed up, or only the x coordinate and the orientation of this bin and the y coordinate will be automatically decided. So let us now determine the displacement analysis of such a mechanism by graphical method. That will be our next. Just now we have seen a very large angle of oscillations of the input and output links of a 3R1P mechanism which is of non-Grashof type. Here is a model which is again a 3R1P mechanism, and this is the Lmin, this is the Lmax, and E is such that Lmin plus E is more than Lmax. Consequently, this becomes a 3R1P non-Grashof type linkage. Let us now observe the angle of oscillations of this link and this link. This is that common tangent that I was trying to draw between those 2 circles. This line is parallel to that common tangent, and consequently this has reached its extreme position. It cannot be further inclined. However, this link can still go, and as you see from this extreme position, it is returning, that is, it is rotating counterclockwise, though this link is still going clockwise. And this is the extreme position of this link, and now it cannot go any further, it has to return. Again it has reached that extreme position and it cannot go any further, but this link can go, and that will, yes, this is the extreme position, it cannot go any further, and this link can still go, and the red link starts rotating in the opposite direction. This is the extreme position of this link, whereas this is the extreme position of this link. From this has to rotate in this direction, it cannot go any further. And from this it cannot go any further, it has to rotate in the opposite direction from here. So for this 3R1P non-Grashof type linkage, as we see, it is a very complicated movement with a very large angle of oscillation for both link number 2 and link number 4. Of this kinematic analysis through the link vectors, let us look at the model of this mechanism, which is a copying mechanism or plagiograph. What we see here, that this is a 5-link mechanism, the fixed link, and there are 4 moving links, 2, 3, 4 and 5. And the dimensions of these links are such that this forms a parallelogram. This link length is equal to this link length is equal to this. And these two triangles are similar triangles, that is, this angle is same as this angle, and this angle is also same as this angle. Now, in this mechanism, we will show later that whatever is the movement of this point, that is reproduced by this point. Only thing, there will be a change in the scale and the orientation. For example, if I move this mechanism such that this point follows this vertical line of this letter L, then this point is also following a straight line, and as we go around this letter L, this point will also draw a L to a bigger scale and a different orientation. The question is that if we are given all the link lengths and the angle of these two similar triangles, then can we find out what is the scale of the reproduction, that is, what is the change in the ratio of the size of these two L's, and what is the angle of these two L's, what is the angle, that is the change in the orientation of this letter L to this drawn L. As we see here, the L is okay, and here it has been rotated by 90 degree almost in the clockwise direction. The question